Good afternoon, everyone. This is Mr. Couple. Today I'm going to be finishing up the ideal gas lesson from last time with showing some example questions of like mathematics and how to work out different problems like that. So after the end of this lesson, towards the end, I'm going to also talk about what exactly is an ideal gas and go into a little bit more details about like the actual mechanics and like physics of the particles and how they move around and stuff like that. But I wanted to first solve some problems using that equation that we derived at the end of last class. So if you forgot, the equation is PV equals nRT. This is called the equation of state for an ideal gas. Some people just call it the ideal gas law, but it's made up of multiple different gas laws, like we learned in the investigations we did last week. So the basic idea is that P is pressure. That's how much force the particles are pushing against the wall with. And then V is the volume of the gas. So we have to find the volume by looking at the dimensions of the container. N is the number of moles. Remember that this is just saying the amount of particles there are. We could, if we wanted to, we could express this as like a kilogram mass, or you could express this as a actual number of particles. But for convention purposes, we just call it the number of moles. That also sets the gas constant being what it is. And if you remember from last time, the gas constant is R equals 8.31. Whoops, no times. Joules per Kelvin per mole. So if we use the different unit for the number of moles, if instead of using number of moles, if we use something else, we'd have to change this R value. And we will talk a little bit about that next week when we talk about the kinetic theory, the molecular kinetic theory of gases, where we'll actually use the Boltzmann's constant in there. But we'll worry about that later. And lastly, T is the temperature. And just remember that this is the absolute temperature, so this has to be in Kelvin. So it must be in Kelvin. If you don't put this temperature in Kelvin, this equation will have all sorts of problems. So make sure that you write the temperature in Kelvin. And if you also don't remember, the temperature is roughly saying how much energy the particles of gas are moving around with. All right, let's do this. So the first question is, estimate how many molecules there are in a gas of temperature 320 Kelvin, volume 0.025 cubic meters, and pressure of 4.8 times 10 to the fifth pascals. Okay, so you can see that we know we're going to be doing, since it's talking about a gas, like the telltale sign, we've got a temperature, we got a volume, and we got a pressure, and it's asking for a number of molecules. So we know that this is going to be an equation of state for an ideal gas equation. So I'm going to start by writing P V equals nRT. We have everything we need except for n. So we need to solve for n. So rearranging this equation to solve for n, we got n equals to pressure times volume divided by the gas constant times the temperature. So all we have to do is just plug into this and we'll get a number. We know the pressure is 4.8 times 10 to the fifth. The volume was provided 0.025. And we're going to divide that by R, which is 8.31, and T, which is 320. So let's go ahead and plug those in the calculator. So here you go. I'm going to open a parentheses, 4.8 times 10 to the fifth, multiplied by 0.025. And I'm going to take all of that and I'm going to divide it by all of this, 8.31 times 320. And so we get that N is equal to 4.513 moles. Now, that's not what the question asked us for. It didn't say how many moles of gas are there. It says how many molecules of gas are there. So we have to convert this mole number, this number of moles, we have to convert it into number of molecules. And so the way you do that is by using the definition of Avogadro's number. I'm going to move this over. So there's an equation we could write this as. I don't think I showed this to you guys last time, so this should be the first time I'm showing you this equation. It's capital N. So capital N is the total number of particles, equals to lowercase n, which is the number of moles, multiplied by Avogadro's number. So we just have to take our n, 4.513, and multiply it by 6.02 times 10 to the 23rd. So let's plug that in. So 4.513 times Man, that looks disgusting. 4 point, let me see if I can reposition myself. Okay, 4.513 times, and now we're going to multiply by Avogadro. Man, why is my things are messed up? 6.02 times 10 to the 23rd. So I just got to take this number, the 5.13, and I just got to multiply it by Avogadro's number. 6.02 times 10 to the 23rd. And I get n is equal to 2. Let's call it 7. Looks like we have 2 sig figs in this problem, so I'll just round that off to 2.7 times 10 to the 24. So that's the total number of molecules in this gas. You will see this a lot with problems with the equation of state of an ideal gas, is that you'll be able to calculate the moles, but then the question is actually asking you for something else. And so you need to make sure that you remember this relationship, that this is how Avogadro's number works. You take a number of moles and you multiply by Avogadro's number, and then that tells you the number of actual particles are. So it'd kind of be like, for a comparison, we can say, you know, if I have 2 dozen donuts, then how many donuts do I have? If I have 2 dozen donuts, how many donuts do you actually have? Well, I have to take the 2 dozen and then I need to multiply it by 12. And so that means that the actual number that I have is 24 donuts. That's kind of what we're doing. We're saying, well, what is a dozen? A dozen is 12. Well, what is a mole? A mole is 6.02 times 10 to the 23rd. So that's all you're doing, is you're just taking this number of moles and you're just multiplying it, scaling it up to find the actual number. Because remember, all that the mole number does is it allows us to express these really big numbers in smaller values. That's all the mole does. And so just don't forget that. It's kind of tricky and a little bit weird, but as long as you remember that it's just a number, then you're good to go. Question number 2. A container of hydrogen of volume 0.10 cubic meters and temperature 25 Celsius contains 3.2 times 10 to the 23rd molecules. Calculate the pressure in the container. So once again, you see the telltale signs that this is an equation of state of an ideal gas. You got volume, temperature, pressure, and number of moles. So like molecules. So we know what we need to do. Now the problem though is that this question is giving us a number of molecules, but the ideal gas equation doesn't have number of molecules in it. It has number of moles in it. So the very first thing we're going to need to do is convert that molecule number. We're going to need to convert that into a mole number. Now doing that is the opposite process, is that we're going to need to divide. So the equation for here will be that the number of moles is the total number of particles divided by Avogadro's number. So in this case, we want to scale it down. So we want to take it from that big number of molecules and divide it down to getting a smaller number of moles. So doing that, we're going to have 3.2 times 10 to the 23rd divided by Avogadro's number, 6.02 times 10 to the 23rd. So the 10 to the 23rds are going to cancel out. So all I have to do is just do 3.2 divided by 6.02. So it's going to be around half. So let's get more precision with that. 3.2 divided by 6.02. So 0.53 and equals 0.53. Let's carry out one more digit, one extra digit. You always want to go one extra than what we have. Okay, so now we know what N is. This question was asking us to calculate the pressure. So if we want to solve for pressure, then that means we have to divide both sides by the volume. So nRT over V. I just realized what's happening. I'm going to take my keyboard off. I was touching the trackpad on the keyboard. That's what was messing up with my mouse input, or my pen input. All right, here we go. So now I'm just going to plug in these numbers over here. So the pressure is going to be equal to, I'm way off camera, aren't I? So the pressure is going to be equal to the number 0.532 times the gas constant, which is 8.31, times the temperature, which is 25 Celsius. That's no good. I need this to be in Kelvin. So 25 Celsius, to turn it into Kelvin, you have to add 273 to it. So that's what I'm going to put in here. So 25 plus 273. I don't want to be in tablet mode. So 25 plus 273. So 298. That's what I need to plug into the math over here. So 298. So we just need to evaluate this. So I'll take my 298 and I'll multiply by 8.31. And then I'll multiply by 0.532. And I got this 1,317. And so that's going to be pascals. And then we're going to want to express this to the two sig figs that we know it to. So I'll just write this as 1.3 kilopascals. So these are examples of just simple plug and chug. Like you just take the numbers, you just plug them in, and then you just work it out. And the things to look out for are make sure that your temperature is always in Kelvin. So if you have Celsius, you got to add that 273 to convert it to Kelvin. And then number two, making sure that you're plugging in the number of moles rather than the number of molecules or some other measurement of the amount of particles that are in the gas. So you just got to watch out for those two things. Otherwise, it's just plugging numbers into an equation, which is pretty straightforward. Let's look at a question that's not as straightforward. A fixed quantity of gas of volume 3 times 10 to the negative 3 cubic meters. It's a pretty small volume. Pressure 3 times 10 to the 5th Pascal, and temperature 27 Celsius expands to a volume of 4 times 10 to the negative 3 cubic meters and a pressure of 6 times 10 to the 5th pascals. So we can see that the volume is increasing. So we're going from 3 times 10 to the negative 3 up to 4 times 10 to the negative 3. So that's what's happening to the volume. So the volume is increasing. And we know from the little investigations that we did that if you increase the volume, that will change the other quantities. But what we're also finding is that when we increase the volume, we simultaneously increase the pressure. So the pressure went from 6 times to the 5th. Whoop, I did it backwards. It started off at 3 and it went up to 6. So the pressure has doubled. So we went from 3 times 10 to the 5th pascals, and we've increased the pressure to 6 times 10 to the 5th pascals. And so the question is, if the original temperature, so if the temperature over here was 27 degrees Celsius, then what's the temperature going to be over here? And it may seem like you can't solve this problem because we don't know how many particles there were. Like we don't know what the number of moles of the gas are. We know that it's a fixed quantity. So that means that it's a sealed, closed container, like no molecules are getting in or no particles are getting in, no particles are getting out. But it didn't actually tell us the number of moles. And if you think about the ideal gas law, where it says PV equals nRT, if you want to actually solve for a temperature like this is asking us for, you don't have everything you need to plug in. Like we don't have N. We have the P and we have the P and we have the V, but we don't have the number of particles. And so it seems like you can't solve it. But actually, you can figure out the number of particles from the original conditions over here. So we have V, P, and N and T, so we can find N over here. So one way of solving this problem is solve it for N, find that N, and then plug it in to the other side. But I'm going to do it a different way. I'm going to do it, I think, as a more powerful way. And so I like to solve any problems like this. They're proportional change problems. I like to solve them in a different way. So I'm going to go ahead and erase all of this. So let's delete that. All right, so check this out. So here's what we know. PV equals nRT. There are two things here that we know stay constant. The number of particles stays constant, and the gas constant, obviously, that stays constant. So what you can do is you can rearrange this equation to solve it for the constant stuff. So I can say that P, I'm going to divide both sides by T, and so I'll have that pressure times volume divided by temperature is equal to nR. But all that nR stuff, that stuff was constant. So what this means is that if you take the pressure times the volume and divide by the temperature, that ratio will always be constant no matter how the gas changes. Since we fixed the number of particles and we fixed the gas constant, well, obviously it's a constant, then that means that the P times V divided by T has to always be the same. So we could sort of create a new equation. I mean, it's not really an equation, but it's valid. We could say that if I take the pressure times the volume divided by the temperature, that quantity will always stay the same. So I know that the pressure times volume times temperature at any one state must be equal to the pressure times volume divided by the temperature at any other state. So I'll just call this state 1, and I'll call this state 2. So pressure times volume divided by temperature at state 1 is equal to pressure times volume divided by temperature at state 2. You'll notice here that we have an equation that we can solve that doesn't have n in it, the thing that we didn't have before. So we can actually just solve this directly for the thing we're looking for. And what we're looking for is the new temperature. So we're trying to find this T2 down here. So all you have to do is just rearrange the variables in this equation to solve for T2. So if we do that, we're going to get T2 is equal to P2V2 divided by P1V1 times T1. So that's a lot of fancy algebra there, but what I basically did is just thought, all right, so this T2, I'm going to move it over to the other side. I'm going to multiply it over to the other side. The T1 is on the bottom of this side, so I'm also going to multiply that over to the other side. That's why I got multiplied over here. And the P1V1, I'm going to divide that over to the other side. And so that's why the P1V1 is on the bottom here. Now what you'll notice is that this ends up giving you a ratio. So the ratio of the pressure and the volumes ends up giving you a multiplicative factor, like a coefficient, that you're going to multiply to scale the original temperature. So all we need to do is we need to figure out what P2V2 over P1V1 is. So I'm going to figure that out now. So P2V2 over P1V1. I'm going to figure out what that is. So I know what P2 is. So pressure 2 is 6 times 10 to the 5th. It's pascals. Times V2, which was 4 times 10 to the negative 3. It's cubic meters. And I'm going to divide that by P1V1. Pressure 1 was 3 times 10 to the 5th pascals. And volume 1 was 3 times 10 to the negative 3 cubic meters. So you'll see here that the units cancel out. Pascals divided by pascals, meters cubed divided by meters cubed. So this is a unitless quantity, which is exactly what we want because we want this number. We want this to be a number that scales or like shrinks or expands or shrinks the original temperature. So let's calculate what this is. So I'm going to do 6 times 10 to the 5th. Okay, here we go. Get out of here. 6 times 10 to the 5th times 4 times 10 to the negative 3. I'm going to divide this by 3 times 10 to the 5th times 3 times 10 to the negative 3. And I get this is 2.667. So now what I know is that the new temperature is going to be, I just noticed that I put a T squared in there. That's kind of funny. What I know is that the new temperature is going to be 2.667 times the original temperature. And the original temperature was 27 Celsius. But we got to be careful because you can't plug in 27 in here. It needs to be in Kelvin because Celsius is not an absolute temperature scale. We need the 0 to be at the correct point if we want the mathematics to work out. So we're going to have to add that 273 to this. And this will give us our answer for the temperature that it goes to. So I'm going to take 27 plus 273. That's 300. I'm going to multiply that by 2.667. So we get 800. And that's it. So the most important thing here, guys, is just realizing what I'm doing over here to build a new equation. So what I'm doing is I'm saying, hey, what's the stuff that's constant in this equation? Solving for the constant stuff, and then realizing that that ratio, that PV over T ratio, is going to stay constant. Now, this isn't just how you solve ideal gas equations. Like, this works for anything in physics. If you have things that are constant, you could solve your equation for those constant things and then set the two sides equal to each other. This works anywhere. It works in gravity, it works in electricity, it works in waves, it works all the time. Here's one more equation. There's one last problem I'm going to solve for you guys. I got 10 minutes left. An automobile tire is filled to a gauge pressure of 200 kilopascal at 10 degrees Celsius. So 200 kilopascals at 10 degrees Celsius. So we want to make sure that we convert the 10 degrees into Kelvin. So that's going to be 273 plus 10. So that's 283 Kelvin. What's going to happen then is you're going to drive the car around. And when you drive the car, the tires are going to be, it's actually kind of complicated. So when the wheels of a car are moving, realize that the tire is actually spinning, and then the weight of the car is pushing down, which is going to cause the bottom of the tire to get a little bit like squished. It's going to squish it down a little bit. But as the tire rotates, that squished part is actually going to move. And that means that as it moves up, it's going to get unsquished. So what happens is as the tires are rolling, as the wheels are spinning, that part, the wheel is basically getting like squished, unsquished, squished, unsquished. So it's going like and that's going to build up friction within the tire that heats it up as that wheel is getting squished and unsquished as it spins through the weight pushing down on the bottom of the tire. So the tire is actually going to warm up as you drive the car. So we should see that the pressure should go up. If we increase the temperature without changing the actual volume of the tire or the number of particles in the tire, the temperature of the tire should go up. The temperature of the tire will go up, and then that will cause the pressure to increase. And if you're not careful, like if you fill up your tire with too much pressure and you start to drive around and the tire gets hot and the gas starts to expand, you can actually blow out your tires. So you got to be very careful when you're inflating your tires to think about the fact that now when the car is at rest and it's cold, you're going to have a lower pressure than when you're actually driving around on the highway. So here's an example of that we're going to calculate. Okay, so then the temperature raises up to, so we want to know what's the pressure at 40 degrees Celsius. And so realizing that 40 degrees Celsius, just to confirm, I don't want to embarrass myself by doing the math wrong. So I'm going to do 40 plus 273. So I get 313 Kelvin for the new temperature. So we start this off just like any ideal gas problem, PV equals nRT. And we look for the constant stuff because this is a change. We see that there's stuff that's changing. The pressure is changing because the temperature is changing. So when you see things like this, where there's a setup where there's like an old pressure and you're trying to find a new pressure, then you got to look for the stuff that's constant. So we have a constant volume of the tire because the tire is not changing its volume. We have a constant amount of number of particles and then the gas constant. So that's all the constant stuff. So we just need to solve for the constant stuff. So if we do that, we're going to divide the t to the other side. So we're going to P over T is equal to NR over V, and that's our constant stuff. So what we have in this case is a lot simpler than the previous question, is we have pressure divided by temperature is equal to constant. So now from that idea, from knowing that, I can set up a ratio that has to always be true. The first pressure divided by the first temperature has to be equal to the second pressure divided by the second temperature. Since I'm trying to find the second pressure, I can just solve for the second pressure. Aaron, did you have a question? Okay, I just heard your mic going off. And so I have this, and so now I'm just going to take my second temperature, which is 313, and divide it by my first temperature, which is 283. And then I'm going to multiply that by the original pressure, which was 200 kilopascals. So 313 divided by 283 times 200. And so I get 221. Let's just call it 220 kilopascals. So the pressure has gone up by 20,000 pascals. It's not a large increase in pressure, but it's enough that it could, if your tire was already inflated up to the limit, that could push it over and that could blow up your tire. So you always have to be careful when you're filling up, when you're inflating the air in your tires of your car, that you don't overinflate those tires. So consider that the pressure is actually going to go up when you drive the car around. So once again, this is a really important concept to remember, is that when you're solving an equation where stuff is constant or when you have proportional changes, this is one strategy that you can use for any problem. You might remember back in the 9th grade, we would have set this up as saying pressure is inverse to temperature. And so you could have like found out what was the proportional change in temperature, take the inverse of that, and that's the proportional change in the pressure. And that's what we did right here, where we found the proportional change in the temperature. We took the second temperature divided by the first, that was our proportional change, and you multiply that by the original pressure. I want to end today, I got like 5 minutes here. I want to end today by just talking about what the heck is an ideal gas. Like I've been using this word all the time, like ideal gas, ideal gas, ideal gas. But what is an ideal gas? Well, in order to understand what an ideal gas is, I want to compare it to a real gas. So there's these assumptions that we make where we say like, not ideal is like an imaginary thing, like it's not a real gas. But it ends up being that it's much easier to create equations and model the mathematically the interactions between particles when we idealize things. So we can ignore a lot of the complicating factors and try to get at like an approximate truth. And that's what we do all the time in physics. So this equation up here is not correct. Like it only works for ideal gases. But it turns out that there's no such thing as an ideal gas. All right, so let's talk about it. So what is the difference between an ideal gas and a real gas? So in an ideal gas, you have like the particles are really far spread out from each other. So there's really low density. There's also low pressure, and you generally have high temperatures. But in a real gas, the difference is that real gases have intermolecular interactions, whereas ideal gases don't. We wanted to ignore all those interparticle forces. Like we said that when a substance turns into a gas, when it vaporizes, there's no more interparticle forces. Well, that's not true because the electric force actually has an infinite range. So those particles will always be attracting each other. They'll always be interacting with each other in a real gas. But to make things easier, to not have to worry about these millions and millions of particles and all the force they're exerting, we just ignore it completely and just focus entirely on the kinetic energy or the momentum of the particles as they fly around the chamber. So a couple of things, these are the assumptions that are the ideal gas. What makes an ideal gas in IB physics is we said that the molecules are really small. They have a negligible size. So you consider them as like dots. So they're the size of the particles is very small compared to the size of the container they're in, or the size of the sample. The molecules all obey the laws of mechanics, so like conservation of energy, conservation of momentum, Newton's laws of motion, all those ideas, the particles obey those laws. There are no forces between the molecules, so that's the big one, that there's no intermolecular forces. The only time that there's a force is when they crash into each other. The duration of collisions is negligible compared to the time between collisions. So the idea is like when they hit each other, it's really quick, and it's a very short time compared to the time it takes for another collision to occur. So the actual time they spend crashing is really, really short. The collisions of the molecules with each other in the container of the walls are all elastic, so we're ignoring any energy losses due like that might be due to like thermal effects. We're just saying they're elastic collisions, so conservation energy applies during the collisions. And then lastly, the molecules have a range of speeds and they move randomly. All right, so let's ask a few questions about this and then I'll be done with this lesson. So question 1. Discussed by the assumption that there are no forces between molecules except when they are in contact can never be true for a real gas. So the thing is that in an ideal gas, we say that there are no forces. So an ideal gas means that there's no forces between particles. That can't be real because in a real gas, no matter how far two particles are, no matter how far two atoms are, they're always going to be attracting each other by these electromagnetic interactions between the electrons and the nucleus of the atoms. Like they're always going to be attracting each other, no matter how far they are. Like if I look at this guy over here and this guy all the way over here, like they are always going to be attracting each other. Even if it's like a teeny, teeny, tiny force, it's not going to be zero. And so that's why a real gas can never be an ideal gas. Like ideal gases are an imaginary, like they're like a fake thing, like they don't really exist. You can get close to it, but you're never going to actually get to it because particles are always going to exert forces on other particles within a sample. Next question. Can an ideal gas be liquefied or solidified, and explain? So here's a picture of what carbon dioxide. So carbon dioxide looks like this. You've got carbon dioxide. So you have a carbon in the center, and then you have these double bonds out to oxygens on the sides. So this is what carbon dioxide looks like. You may have studied this in chemistry. If not, it's fine. But can carbon dioxide become liquefied or solidified? Well, here's what carbon dioxide looks like when it is. That's dry ice. So like you guys have all probably seen dry ice. Like carbon dioxide can be solidified. But in order to be a solid, that's my time. Stop. Okay. In order to be a solid, the particles have to be exerting forces on each other. That's what makes a solid, is that the particles are stuck together. So can an ideal gas be solidified? And the answer is no. So interparticle forces or intermolecular forces are needed to be solid. So an ideal gas, no matter how cold you cool it down, no matter how much energy you remove from it, it is always going to stay as a gas. Intermolecular forces are needed to be solid. And the last question, are there situations when a real gas behaves like an ideal gas? And the answer is yes, but notice that it says behaves like. So it means there are situations where the differences between a real gas and an ideal gas are negligible. So your answers, although wrong, will be approximately correct. And those situations are, let me move this out of the way. Those situations are, get out of there, when you have, so this is a real gas. So this can never be ideal. This is real. But an ideal gas can exist. So to be ideal, we generally say you have the following criteria. You need low pressure. So we can see that we have a low pressure compared to the real gas because there's fewer particles pushing against the walls. You also have moderate temperatures. And remember, that's because they can't become solids or liquids. So we want to make sure the temperatures are staying high. And then the last thing you need is you need low density. And so the idea is that if the particles are far enough spaced apart from each other, they'll be so far that they aren't able to get close enough to exert those intermolecular forces. So if you keep the gas particles at a low pressure, spaced out and moving fast, you can get very, very close to being an ideal gas. But anything that's not these, PV equals nRT will not work if it's any other conditions. So PV equals nRT, the limitations are you could only use this for these situations. Okay, that's it. I hope you guys have a wonderful day, and I will see you next time.